I mentored Nick. Oh, hey, we're recording now. I mentored Nick on this careful experimental work in which he became highly proficient. And I was very grateful for that because ultimately a lot of his data was data that I used in my doctoral dissertation. So I have worked extremely closely with Nick because that's a very important thing for a graduate student, their doctoral dissertation. And one thing that I can very safely say is he is extremely proficient in all of the aspects of this work, from acoustic signal processing, which topic he presented on at a conference in our field called QNDE in summer 2016. We actually hosted, Georgia Tech hosted, so that's a particularly impressive thing for an undergrad to do, is present at a conference that we are hosting. And we work closely in hands-on lab work, calibration of equipment, programming automated processes, simulation of results, synthesis of data and models. I mean, you name it, it was full stack. And I got to see Nick's extremely dogged determination, very, very tenacious researcher. And I'm particularly sorry for some of the nightmare data collections that I put Nick through. We're talking several hour-long data collections, most of it by hand, some of it automated. But I also got to see his sharp insight and an extremely practical aptitude for problem solving. Really just, I was extremely impressed. Nick was without a doubt the best undergraduate researcher that I had the pleasure of working with. And that was one of my roles in that lab, was working with undergrad researchers. Then he went off and left us for MIT and only did more successful stuff there. I was doing a little bit of light stalking on Google Scholar and LinkedIn as this was all unfolding, several publications to his name. And when I saw this poster for Nick as director of engineering at Renewvia, I was not surprised that I would see Nick in a position like this, and I was thrilled to see that he would be coming back to Georgia Tech to talk about his work. So all of that to say, this is a very cool moment for me, for hopefully for Nick to be able to do this, and also for all of us, because we get to hear about a truly gifted Georgia Tech alum. So Nick, please take it away.
I'm so honored. It was getting to work with David was perhaps the highlight of my undergraduate experience. And I, in my own doctoral work, inspired by David's mentorship, I got to take on 10 undergraduate researchers of my own, which was probably more than I should have. But yeah, whenever I was struggling with that, I would always just ask myself, like, what would David do? Like, how would David handle this situation? So yeah, I'm going to ask really quickly two favors from the host of this Zoom session. The first is to please allow me to screen share, if you wouldn't mind, so that I can share some slides, because I would absolutely love to show you guys pictures of kind of the work I've been doing and things like that. And also, because I am currently in Lagos, Nigeria, sometimes the internet is not the most consistent. So if I do start to sound like a robot or just very garbled and not understandable, I would also ask that one of the hosts of this conversation please interrupt me and and make sure that I stop until my internet signal recovers. So I will. Perfect. Thank you. I appreciate that, Professor Torello. Let's see. So yeah, what is the best way for me to become able to share my screen? Should I just hold on here or log out and log back in?
Give me 1 second, Nick. I'm going to update the settings now. While I'm updating the settings, Nick, you can feel free to forward the slides to me and I'll go ahead and share them for you until we have.
That's an excellent idea. I can definitely do that. The slides are 50 megabytes. I didn't realize that I had put that many pictures into this presentation. I will try to press that so it is realistically sendable.
No worries. I'm still updating the settings on my part as well. My apologies. I thought they were already updated, but I appreciate your patience.
Not a problem for me at all.
It's good to know that some of the very seemingly mundane issues I have in the class with sharing material is widespread. So this is more encouraging for me than anything.
Much better. I have officially sent them to you, Courtney. I saved it as a PDF and that cut down the size enough.
Perfect. As soon as I get them, I will open up. I'm refreshing my email. Nothing has come in yet, but I will open them up as soon as possible. If you want, there we go. They just came in.
Perfect timing. Perfect. Thank you so much, Courtney. I really, really appreciate you doing that. Sorry, I made my PowerPoint so big. It made you open that as a PDF. I am also, to preserve my bandwidth, I am going to also turn off my video while presenting, and then I'll just say like slide or go ahead and move to the next one when I want you to advance. But anyway, like Professor Trello said, my name is Nick Selby. I'm the Director of Engineering for Renewvia Solar Africa, which is an African solar minigrid company. I'm based in Nairobi, Kenya. Yeah, like I said, if there's any robot noises coming from my end, please just tell me to stop. I am in my role, I am responsible for the design, procurement, construction, productive use, and software infrastructure of solar mini grids in rural Kenya, Nigeria, where I am right now, and also Ethiopia. I'm also a tech alum. I graduated with a bachelor's in ME in 2016, and before I launch into what life building mini grids in Africa is like, I thought it would be a good idea to show you what I did while at Georgia Tech. Please advance to the next slide. I love to travel, and I use and abused the Office of International Education while I was at Georgia Tech. I farmed rice paddies in China, kayaked in Scotland, mountaineered in Antarctica, all on Georgia Tech's dime. Please advance. And when I wasn't traveling or in class, I divided my time among the solar car racing team, undergraduate research, TAing for CS 1371, and also church activities. And I'm sorry, Professor Trillo, I realize I don't actually have a picture of us. Otherwise, it definitely would have gone on this slide. But please advance. My time at Georgia Tech was filled with wildly fun experiences, but between football games, going viral on YouTube, starting a company. And after I graduated, I started grad school at MIT. Slide. Similarly, I had a lot of adventures while getting my PhD. I continued to travel. I got to do research in robotics and machine learning. I helped start a union, donated a kidney, and after I graduated, I started working with the National Science Foundation I-Corps program to spin off my PhD research into a startup. I ended up raising a little over $500,000 in seed money to launch this business. And that's when I heard about this job. I tend to spend a lot of time thinking about my impact on the world around me. I think I would be very uncomfortable working for a military contractor, Wall Street Bank, and I do believe that my little robotics startup did have the potential to help people, but like rural electrification in Africa with solar power and also a position in this company that allows me a lot of creative freedom to use those Georgia Tech skills to innovate was too exciting to pass up. So I gave back the money I had raised for my startup, packed my bags, and moved to Nairobi. Interestingly, though, I did not actually get to stay in Nairobi very long. Slide, sorry. My first project with the company was to co-manage the construction of a mini-grid at a refugee camp in northern Kenya for 3 months. And it was quite the challenge, but in a really fun way. Slide. Every day I would bike to work at 8 a.m. Avoiding the obstacle course of camels on the road was a great way to practice riding a motorbike, which I had never done before. Slide. And at the work site, engineering problems were, oh, actually, sorry, slide, you had it. Thank you. Yeah, the engineering problems were surprisingly related to a lot of the stuff that you learn in engineering classes. So for example, sometimes monsoons involve 60-mile-an-hour winds that would pick up solar panels and throw them 100 meters into a tree. So like, for example, how big do we have to build our racking foundations to be able to withstand that sort of force? And the answer is you draw yourself a free body diagram, you look up some fluid dynamics models, a drag force of wind on rectangular surfaces, you calculate your reaction forces, and you use a simple soil model to design a concrete structure that can resist those forces and moments that you calculated. And the coolest part is that it works. Like if you do the math right, your solar panels, they'll stay exactly where you want them to, even when a virtual hurricane assaults your mini grid. And that is a great feeling when the math actually becomes reality and keeps people and your equipment safe. Slide. It's a ton of fun. And I've been learning a lot about not only how to solve these more practical engineering problems, but I also get to apply more of my mathy background in building better engineering design tools to allow us to build better mini grids, faster, and scale our construction output. Slide. I'm really proud of what we built. When I left the settlement, we had connected 1,000 customers, and now we've connected almost 3,000 customers in the camp, and started working on a future expansion plans to supply power to more of the 200,000 people in that area. Slide. Kenyan food is limited but delicious. Every day for lunch while I was in the camp, I had one of two meals. This one's my favorite. It's an Ethiopian lentil stew called adis. The other is a black beans over chapati with a side of sukuma wiki, which is a vegetable related to collard greens and is also delicious. There's also a lot of meat options with goat, mbuzi, camel, ngamia being particularly popular in the region around the refugee camp. Quite tasty. Slide. Often, our workdays included visits from various international organizations interested in our project. These included the UN Refugee Group, GIZ, which is kind of like the German version of USAID, and the World Food Program, as well as a few others. Slide. For work, we'd usually go hiking. There's some decent bouldering in the area, and as long as you leave before dark, you can watch a beautiful sunset. And if you're willing to risk staying a little after dark, the stars are also amazing. Slide. Getting into trouble while adventuring is also pretty fun. One evening while exploring the town, I got propositioned, which is exciting. On a different night, my colleague and I were walking around getting high, and we weren't really paying attention to the time. and we were talking to this one local woman when it started to get dark. And we noticed this group of men approaching us, and the woman gets all serious, and she told us that they wanted to fight us. And then she goes, "Here, let me have your water bottle." She grabs my colleague's water bottle and starts running away in what I can only describe as in the style of Monty Python's like Ministry of Silly Walk, somewhere between like a waddle and like with her arms like shaking at the side in rhythm. My colleague and I looked at each other and then just booked it in the opposite direction. We ended up being fine. A group of men like probably didn't care about us at all, much less wanted to fight us. It was just absurd, and we had a good laugh. It's important to me to highlight, obviously all these fun and goofy parts of my life, but many of the Nautilus experiences are less fun. For example, racism is rampant in Turkana County, where this refugee camp existed. There's an instance where a drunk Turkana driver hit and injured a South Sudanese woman living in the camp. A group of South Sudanese refugees decided to retaliate by killing a random Turkana guy they found the next day. And then a few days later, a group of Turkana killed another random South Sudanese man. And this kind of escalation series happened a couple of times while I was there. The first time concluded with a large and bloody machete battle near the construction site while we were working. And the second time stopped early because the Kenyan Telecom turned off the service of every non-smartphone in the area so that no one who could only afford a flip phone could coordinate attacks over text. And that was wild to me. But a lot of my Kenyan friends to whom I tell this story react like it's nothing. So, yeah, that makes sense, which is even wilder. One of the more overwhelming parts of this job is that these kind of ethical conundrums seem to pop up every week or so. And I've been very thankful for the friends in my life to whom I've talked a lot about what I can do in these situations, even if the answer is often just nothing. Slide. After we finished the construction project, I got to settle into my new life in Nairobi, which is my favorite city I've ever lived in. And I really liked living in Atlanta. Slide, please. The first thing that's great about Nairobi is that the weather is always 70 and sunny. There aren't any seasons because we're at the equator, and on the few occasions where the temperature has reached like 60 degrees, all the Kenyans bundle up as if they're like in Atlanta snowpocalypse. There's a ton of fun stuff to do in addition to kind of more traditional safaris. Nairobi National Park is located in the middle of the city. For whenever I want to go see like a lion or an elephant or something, I got to feed a giraffe from my hand, which is great. One perk about the weather always being nice is that there's never an excuse not to have a house party. The music scene is also great. I've gotten into Afro house in the past year, and the concerts and festivals are fantastic. The nightlife in general is great. There's plenty of great bars and clubs. The food scene is excellent. Nairobi has like major grocery chains and restaurants serving food from around the world. There's plenty of great hiking and backpacking nearby. The beaches along the coast are divine. And just like with any other city, there's definitely dangerous parts of it. I've never been in a situation where I felt unsafe in Nairobi. You just gotta be smart about it. Most people in the city do speak English, which is nice, although I've definitely enjoyed learning Swahili, which is a relatively easy language to pick up. Also, everything is cheap. The purchasing power parity relative to the dollar is out of this world. So for example, like an hour-long Uber ride, $12. When I get lunch from the stand down the street from my house, I'll get like a big bean stew with cabbage and hot peppers and chapati and like sliced avocado with a cup of chai for $1. Fantastic. Slide, please. Because my work never stops sending me on adventures. In addition to kind of more traditional engineering design, I really enjoy getting to do some of the more hands-on engineering. Usually this is involved in training my technical staff to perform various maintenance tasks. I also get to interface a lot with community leaders and customers to hear their concerns and desires, and then translate those desires into design decisions. Slide. Yes, because you are tech students, I feel like I can talk about some of the high-level engineering design behind mini-grids. Solar panels themselves are rated by power output, like you might have like a 300 or a 500 watt panel. But interestingly, you pick how many solar panels to install based off of your energy needs, not your power needs. So because you can't, because you can't rely on your PV all the time. Like if there's clouds or nighttime, the battery inverter is actually probably the most central piece of equipment in a solar mini grid. Like it is the device that actually forms the grid, that shapes the AC waveform that gets sent out along the power lines to people's homes. And thus, the battery inverter is the first piece of equipment that you pick once you know what the load profile looks like. The battery inverter must be able to output enough power to meet the maximum power demand. And the battery inverters that take that energy not actually directly from the solar panels, but from the batteries. And therefore, you size your battery bank based off of the amount of time you want to be able to supply power without any input from your PV. So for example, if you want to be able to supply the load for like 12 hours every night with no sunlight, and the average load during that time is 10 kilowatts, then you will need at least 120 kilowatt hours of battery storage, plus a little bit extra so your batteries don't have to deep discharge at all. And then after all that, you can finally design your solar array. We typically use some in-house simulation design tools to simulate the amount of energy produced by PV given the irradiance data for the location that we want to build. In addition to the number of panels, you also want to pay attention to how many you connect in parallel and in series, which I guess we can talk about later if you want. Also, you can't just connect the solar panel terminals directly to the battery bus bars. Instead, we use devices called charge controllers to smooth out and control the so-called wild DC from the PV array to optimally and safely charge the batteries. And the number of panels you need to generate the energy necessary to supply the load governs the number of charge controllers that you have to buy. This system that you see here that I've just described is the simplest possible architecture for solar mini grids because the energy flows in a straight line, right? You have light, it's the solar panels, which charge the batteries, which power the battery inverters, which supply the loads, all one line. So this architecture is called DC coupling because you're converting the power from the solar panels to a nice DC supply to charge the batteries rather than feed the AC load directly. And in this system, energy is flowing in one direction, but battery inverters are bidirectional. So many mini grids often also have a diesel generator backup that can be automatically turned on if the batteries get too low. And since the generators output AC, they can be connected directly to the AC output of the battery inverters. And the battery inverters can actually rectify excess AC power and use it to charge the batteries if necessary. Which brings me to AC coupling. So instead of using charge controllers to charge the batteries directly, you can instead connect your array to PV inverters, which convert the DC power from the panels directly into AC power for the load. However, unlike battery inverters, PV inverters can't form a grid by themselves. They can only add to an already existing grid. But just like for a diesel generator, battery inverters can rectify excess AC power from PV inverters to charge the batteries. And that type of architecture is called AC coupled. Because power from the solar panels is converted into AC directly. You can also have both PV inverters and charge controllers in the same system, and that's called hybrid coupling. As a general rule, DC coupling is more efficient if your loads are primarily at night because charge controllers are more efficient at charging batteries, and AC coupling is more efficient if most of your loads are during the day because you can feed the load directly from the batteries. Slide. And now that I've talked your ear off about flows of energy, I should also talk about flows of capital. So first, the company that I work for, Renewvia, is a for-profit enterprise. It's actually based in Atlanta. It does like commercial solar kind of around mostly the Southeast United States. We have investors and stock, and if we don't do a good job building mini grids, we don't get paid. At first, when I started this job, this worried me. The ability for people to have power was dependent on a for-profit company. But it turns out that our financial incentive to keep mini grids running smoothly for decades, at least relative to kind of a nonprofit model, actually does a decent job at enabling reliable power for communities. Our main source of revenue is pretty much the same as an American utility company. We meter each of our customers and then charge them money per kilowatt hour of energy they consume. So the amount of money that we charge varies significantly by location, anywhere from like 10 cents to 60 cents per kilowatt hour. For reference, I think it's about 11 cents per kilowatt hour in Atlanta. And anyway, the tariff is driven by four main factors. So the first is economies of scale. There are a handful of sunk costs whenever you build a mini grid, like building a powerhouse, clearing regulatory requirements, things like that, that come with every mini grid. So the larger your community, the larger the optimal generation size, the less money you're spending per connection or per kilowatt of PV. And therefore, it behooves us to find big communities with significant commercial activity. The second factor is price elasticity of demand. So in the US and Europe, we often think of demand for electricity as inelastic. And by that, I mean that if the price of electricity doubled, you'd still want to keep your AC running in the Atlanta summer. But in rural Africa, that is often not the case. So sometimes by charging a little bit less for electricity, you actually drive up quantity demanded so much that your total revenue actually goes up even though your price went down. And this is something that I think a lot of the mini grid industry doesn't understand yet. A lot of companies either just charge the maximum that they're legally allowed to, or they'll charge so little that they just run out of energy every night. But I argue that tariff optimization is actually so important that I include it as a design variable in my mini grid optimization process. The third factor that drives tariff is that solar mini grids are relatively easy to maintain. Most of the OpEx tends to come from distribution network, not the generation equipment, just taking care of the poles and power lines. However, the capital required to build the project is enormous. Even small mini grids can cost hundreds of thousands of dollars to build. And I'm working on a proposal right now whose total capacity capital cost is over $7 million. Renewvia doesn't have that kind of cash just lying around, which brings us to the final factor, capital financing. Before we build a mini grid, we have to get the money to do so. We always, try to get grants or subsidies, which obviously help, but they never fund a project 100%. So we fill the gap with equity and debt financing. Debt is pretty simple. We get a bank to lend us money and then we pay it back with interest. But commercial banks in Africa are still scared of the mini grid market, and they don't like lending money to projects like these. Equity is popular, though. Investors can buy shares in a mini grid that guarantee them a percentage of the profits of the mini grid, kind of like how one might invest in a stock that pays dividends. And the better terms we can get for equity, debt, and grant financing, the lower we can set the tariff. And that's all I care to get into for mini grid financing. I tend to prefer focusing on the engineering side of things because that's where my strengths and frankly my interests lie. But I can tell you that we typically aim for an internal rate of return around 20% and a multiple of invested capital of around 2. Slide, please. Yeah, that brings me to today. So some of the projects I'm working on right now, slide please, that I'm excited about include expanding the refugee camp mini grid I talked about to become the largest in East Africa and serve over 200,000 people. Separately, building the largest mini grid in Ethiopia to provide irrigation for farmland. Building 23 new mini grid sites and electrifying 50 United Bank of Africa branches across southern Nigeria, with solar, which is why I'm here now. Using my machine learning background to optimize the design of solar mini grids, launching a blockchain-based carbon asset to provide additional revenue for African governments interested in renewables, and publishing the first comprehensive peer-reviewed social impact assessment of mini grids in Africa. Slide, please. Yeah, and with that, I will open the floor for questions. Oh, excellent. A Q&A box.
So people can ask, I'm going to ask a quick question, Nick. This is a great journey. I think what you're trying to do is really a social impact. So the question which I'm looking at this is right now, what's your plan for scale up of some of these technology? And where do you think is the biggest challenge in scaling this up to even some of the remote areas in developing countries in India and others, which have similar challenges?
Definitely. Yeah, scale is a huge factor for mini grids, right? Like if we can build a bigger mini grid in one community, then we can drive down the cost of that electricity for that community. I think there's a few different answers to this. The first is just better engineering optimization. I've noticed that among kind of my peers in this field, there's still a lot of engineers using kind of like rules of thumb to determine, how to build the best mini grid. And I think that like stuff like that kind of bothers me. I'm a Georgia Tech student. I want to do that. I want to like figure out what is optimal and then prove that it's optimal. And like that's the way that I want to design and build mini grid. So I think number one is kind of moving into a more rigorous design optimization process as a like mini grid developing community. And I've actually, in talking to my peers about this, I've gotten some excitement on this front. So I think that's definitely a likely kind of next step for this industry. Another thing is productive use. So you can imagine, you build a mini grid and you oftentimes are designing your mini grid for what you expect the load profile to be. And we can use a lot of data from mini grids that we currently have running, ideally in the same region, develop an understanding of how we can expect those load profiles to look. If you can do things like, for example, connect your future customers with companies that create appliances, electrical appliances, and then also companies that can help provide financing for those appliances, then you can drive up your load profile, which allows you to build much bigger mini grids, which allows you to drive down the cost of electricity to the user. So it's this like really wonderful like scaling solution here. And so if you can, so for example, we work in a lot of communities that are very dependent upon charcoal for cooking, right? So if we can connect those communities with not only electricity, but also manufacturers and financiers for electric pressure cookers, which we've done in a couple of our sites, that can be a really great way to encourage people to use more electricity. Electric pressure cookers consume a ton of power, like it's like sometimes over a kilowatt, which is great. So that's one way to do it. And then, like there's also, we work in a lot of communities that are near lakes, a lot of fishing communities and places like that, and providing machines to make ice to keep the fish cooler longer and kind of promote the growth of that industry. Therefore also promotes the consumption of electricity because, just like with electric pressure cookers, ice makers use a ton of electricity. Compressors are very hungry for energy. And so that can also be, those are great ways of doing it. And I think the last solution that is perhaps like most potent for scaling is financing. It's really, really great, like I said, when we can get like grants or subsidies. The more governments and kind of international organizations can get involved in promoting the construction of new solar projects, the better, the more that debt sources like banks can become more comfortable with. You can get like amazing rates of return and ROIs, but you have to wait like 20 years maybe before, like mini grids last forever. And so it does take, not 20 years, that's a way over exaggeration, but it does take a while to like actually make those amazing returns. So we can get debt more comfortable with those longer timelines, even though you can still achieve like excellent IRRs, the better. I see a question.
So,
oh, sorry.
I was just going to read the questions in the order in which they appear.
That's so much easier. I appreciate it.
Not a problem at all. So we have a question that came in. It says, what type of stationary energy storage devices are you using in these mini grids? Specifically, what type of batteries? And if you're able to elaborate, of course.
Definitely. So Renewvia uses almost exclusively lithium iron phosphate batteries, LifePos. They are really great. They have a high energy density. They're pretty safe. It's fantastic. Some mini grid developers are using are using lead acid batteries, specifically flooded lead acid batteries. I don't think. I think that's generally, not always, but generally a bad idea because you can only get about a 50% depth of discharge if you want those lead acids to last a while. And that typically overwhelms the slight reduction in like dollars per kilowatt hour that you're spending. What I am excited for is some interesting new battery technologies, some interesting new battery chemistries are starting to make their way onto the scene. So like the great benefit of lithium ion in general, LifePo, but like more generally lithium-ion battery chemistries, is that they have a very high energy density, and by that I mean kilowatt hours of storage per unit mass. And that's fantastic if you're like, if you're building like an electric car or an electric bus or something, because you want the mass to be very, very small, but the energy to be very, very high. As a mini grid, we don't really care how heavy the batteries are. They're just going to sit there in your powerhouse all day. What we care about is kilowatt hours per dollar. And so there's some really interesting new chemistries that are coming out. The one that I saw recently that was particularly exciting was a vanadium redox flow battery that has significantly less dollars per kilowatt hour, even though they also have less kilowatt hours per unit mass. It doesn't matter, because like what we care about is spending a low amount of money in order to achieve the same goal. So yeah, that's a very long answer to your question, but that's what I feel like on the battery side.
Thanks for sharing that, Nick. All right, so the second question comes in from Dr. Bross, one of our associate chairs here in the school. And his question reads, what is your experience with local maintenance for your mini grids? My father did some work in Africa decades ago, and there was always a problem with the maintenance of Western equipment by local people. Do you have similar issues, or do you have good local technical support?
Great question. Also, hi, Dr. Bross. It's wonderful to have you here. I'm really excited. Big fan of Dr. Bross. There is, yes, definitely we have a lot of problems on the operations and maintenance of local mini grids, right? Because we not only like engineer, procure, construct the mini grids, but we also have to continue maintaining them throughout their life. We often own, like Renewvia maintains ownership of a part of all the mini grids that we build. So yes, that is a very big problem. I would say I would be very surprised if this were a problem that was like specific to African contexts. Like if you gave me responsibility of a mini grid without teaching me anything about it, like I wouldn't know what to do. And that is definitely also the case here, where training of the local site agents and local technicians is of utmost importance. So we spend a good amount of time and resources developing not only like robust training and education for our site agents and technical staff that are local on the ground, because it is very important, not only from a financial perspective, but also just like from a community relations perspective, to keep the operation of the mini grid in the hands of local people who actually use it. So yeah, like a lot of training and education resources, but also infrastructure resources to make it very easy for them to report any problems that they have and receive technical support from our engineers who are based in larger cities, or me if need be. Yeah.
So Nick, those are the only two questions that came in
Excellent.
in our chat. I don't see any additional ones. Oh, actually, there are two more that just came in.
Perfect.
So, all right. All right. So the first one I'll read is from Daniel. It says, hey, Nick, thanks so much for this presentation. What are some of the base factors that you evaluate when determining a site to construct a new mini grid system?
Yeah, that's a good question. I have this dream in my head where the pipeline development process for mini grid companies is like an AI that just scrolls through like Google Earth and like evaluates a community based on apparent size and like amount of possible commercial activity. Until then, we have a really robust pipeline development team. So people who oftentimes it's like connections, like somebody knows somebody who knows somebody who knows about a community that like is up and coming, or like it's still very rural. It's still, all of the mini grids that we build are nowhere near like the national grid's electric power lines. Oftentimes that's mandated by regulation. But a community that's kind of like large enough that if we built a mini grid, we could then sell power to people in that community for a reasonable rate. And that's kind of like, in general terms, that's where I want to build everywhere, but like I especially want to build in places where we can build a power plant that can provide affordable and reliable power to the community. So that's broad terms. And then kind of like how we actually determine that is through design optimization, right? So once a community that is identified that wants power, that wants to be electrified, and it might be a good fit, we start having those meetings with communities, figure out kind of what their desires are, why they want electricity, what they want to use electricity for, and then turn those into design decisions, right? How big would we have to make a system in order to do that? And we use an iterative design process, kind of building a mini grid for that load profile that optimizes, sometimes internal rates of return, or how cheap we can get the tariff to go, in order to kind of give a score, if you will, to that community. And then we can use that kind of score then to prioritize, well, we should, build in this community first because they have a lot of commercial activity and they're really big. We would be able to provide power to a lot of people. Our resources could go, like our time and our energy could go into designing a system that would be really, really great right there. Also, one more point to add on that is that we have really good relationships with local regulators. Oftentimes governments will maintain at least some kind of lists of like a wish list of communities that they want to electrify next for, and they have similar goals to us. Very helpful.
Great. All right, so our next question comes from Dr. Torello. It says, do you find that there are local entities or not-for-profits that are also doing this work that you can partner with, or is this mostly fueled by international development work?
Yes. Not so much nonprofits. Usually the capital requirements for this are too big for nonprofits to chomp. You can kind of imagine like if a do-gooder engineering group wanted to build a mini grid, it would be rather difficult for that nonprofit oriented organization to then like seriously invest in maintaining that mini grid that they built. Like it's really sexy and like, ooh, great, you built a mini grid, but then like actually keeping it running for 20 years is like a whole different challenge. And it's not quite as like, oh, my mini grid kept running today, or at least for most of today. Like that's not as exciting for nonprofits sometimes. But we do partner with local mini grid developers. Oftentimes, like local mini grid developers are much smaller and less well resourced than us. But in one of the communities we serve, very, very large community. It's like, oh, the refugee camp. Sorry, the refugee camp that I was talking about. There's two other mini grid providers, one run by a local Kenyan man and one run by a Congolese refugee. The three of us together kind of help each other a little bit. They often provide, political connections and licensing, but neither of them have any technical team. So Renewvia is able to provide kind of its engineering expertise. So if they have a problem with their mini grid, we can kind of like come in and show them how to fix it. That's very helpful.
I don't see any additional questions. No one else is sneaking any others in.
All of those are really good questions. Yes.
I'm gonna sneak in and ask another one. So right now there's a lot of funding in this space coming from World Bank.
Yes, it's true.
But the requirement to get to the World Bank and trying to do it is very narrow in some way. They are really looking at certain things. Do you see a public-private partnership in this space with World Bank? And that's where like Gates Foundation, others can really drive this. And if that's the way, how Georgia Tech can do things where we can create a program which can support those kind of activity to work together. Do you see a role like university can play in this space?
Yeah, that'd be awesome. We should talk like after this and like kind of like brainstorm together because I love that idea. The PPP laws just like systems, I guess, in the countries in which we operate are still kind of up and coming. There's definitely a lot of interest from the government to like build systems like these, but it's very, just like with any government processes, it's often very, very slow to really get off the ground and build that infrastructure in such a way that everybody is happy with it. But yes, absolutely. Like I love the idea of universities getting involved to like help facilitate the creation of those, especially because, as you said, the World Bank is throwing a lot of money at this and similar projects. as well as a bunch of different organizations. We're doing a very large project right now, negotiating with the African Development Bank, which is similar in structure to the World Bank, for debt financing.
This is really good. So I'm going to ask one more, and that's not on the sign.
Please.
Based upon your journey going from here, what do you think was something Georgia Tech prepared you, and you say, I really took that one in my day-to-day learning?
Definitely. So many. I mentioned during the beginning of the talk that I was actually surprised like how relevant coursework at Georgia Tech was to like everyday engineering challenges, including like, keeping your solar panels fixed to the ground, even though there's like a heavy wind blowing, while also not spending way too much money on concrete for your foundations. You really do draw. I really do find myself like doing a decent amount of calculus, like on a day-to-day basis. I really do find myself drawing the free body diagrams on a day-to-day basis, and like using my Kirchhoff node and loop rules to like figure out how to design better electrical systems. It's math works, guys. It's really great. You should use it. Another thing that Georgia Tech prepared me for, and actually specifically my work with Professor Torello really prepared me for, is the ability to ask kind of new and innovative, like scientific questions to push the field forward. Like this is definitely, minigrids in Africa, definitely an emerging market. We're actually, the market is so small that many different minigrid developers, we don't really compete with each other so much as like, we're all like helping each other out. Like we've got group chats and everything on WhatsApp, like, oh my gosh, see what this organization did, or how did you build this? And we're all very open with each other. It's great. And kind of with that spirit of collaboration, we can all collectively ask really great scientific questions and frame them in kind of the rigorous, robust research frameworks that you might do in an undergraduate, in an undergraduate research project, or at least hone those skills, right? And that can really also be a way to push the field forward and to eventually like bring more social impact and more affordable and reliable power to your customers.
Thank you, Nick. This has been a great discussion. I really like to see what you're doing. What you're doing is what we say in our Georgia Tech mission is about improving human condition, and you are really doing that. So thank you for everything you're doing and sharing your time with us. Can you still hear us? Nick, can you hear us? Courtney, can you hear me?
I can definitely hear. It looks like Nick may have frozen on his end a little bit. He's moving slightly. Okay. And it looks like he's speaking.
I'm so sorry. Yeah, I cut out for that, but I heard bits and pieces, and I really appreciate it.
Yeah. And the last one I'll say, I'm still waiting for my iron suit. Whenever you make my iron suit, I want to have that so I can do it. So with that, thank you, Nick, again. And I know it's probably evening there, so have a great evening.
I think he might be freezing again, but again, I just wanted to thank everyone for logging on and joining us today. Before we end, I'm just going to share my screen so you all can see when our next Emmy speaker series will be held. We have 4 coming up for the rest of the semester. On April 11th, we'll have Ahmad Haider. On April 13th, Anne Marie Cardwell. April 18th, our very own Roxanne Moore. And April 20th, we have Chris Herman. So feel free to go ahead and scan the QR code that's shown on your screen, and you can RSVP for any one of those upcoming talks. Thank you again for joining us today. Nick, have a great night. Thank you again for joining us this evening. Afternoon over here, but maybe evening where you are.
Thank you so much. I really appreciate it.
Of course.
Thank you, David, also for the introduction.
Oh, yeah. Thank you, everybody. Thank you, Nick. Thank you, Devesh.
That was really special.
Yeah. All right. Take care, everyone.